So in the other section, I'm not sure if we had the same stopping point. In the other section, we got to this problem here. Does this look familiar? Okay. Did we get through it or step 3? Perfect. Thank you so much. All right. So what I'm going to do is I'm just going to start from here. We'll talk about what the first couple steps are, and then we'll finish it off. So taking 1 second to review what it is that we have done. So Chapter 5 is about Thevenin and Norton equivalent circuits, okay, which you can also call equivalent sources. They're equivalent to one another, right? Thevenin is composed of a voltage, internal voltage with a series resistor. The Norton is an internal current with a parallel resistance. We know that we can switch back and forth between those two, which is an interesting characteristic. But what is a little bit more important or interesting to us is the fact that we can take more complex circuits and we can boil them down to one of those two. So how do we do that? In the last class, we found the equivalent for a linear circuit with only independent sources. I forget if it was independent voltage and current or if it was just independent voltage. I think it was both. And so what we saw was for that type of circuit, that's like our base case. A lot like how when we talked about nodal analysis, our base case was current sources and resistors. This is sort of our base case for the Thevenin. Independent sources and resistors. So the way that we did that, maybe I could ask you, there was really just 2 steps. If you eliminate all the labeling and making sure that the circuit fits the requirements for finding a Thevenin or Norton equivalent, what were the 2 main steps? You have to figure out 2 values, right? There's the Thevenin, the internal voltage, and then the source resistance, RS. How did we figure out RS? I'll start with that one. Anybody remember? So what we did was we applied superposition, and we know that we can solve the circuit with and without the sources independently. So in order to find the RS, we shorted out our voltage sources, we opened up our current sources, and then we simply calculated what the equivalent resistance was between the A and B terminals, right? In that case, I believe it was 2 resistors that were in series. How did we come up with the Thevenin? So what do we know about the Thevenin? If I scroll up for 1 second here, if you take a look, what you see is that the voltage observed at the terminals, which is we're calling VL, is the same as the internal voltage Thevenin, as long as there's no current IL flowing, right? There's no voltage drop across RS, and that means that VL is equal to VTH, right? So if we want to figure out VTH, we can do what's called an open circuit test, okay? Or analyze the circuit under no load condition. We don't connect anything here. We solve for what the voltage is at VL, at the terminals, and then that is, by definition, what VTH is. So those are the 2 steps, the main primary 2 steps. Get rid of all the sources, solve for the equivalent resistance, that's RS, put the circuit into an open circuit, no load condition, okay, analyze that circuit, whatever the terminal voltage is, that's VTH. Okay, now, moving on to what we're doing today. So what you see is that this circuit has a dependent voltage. That screws up step number 1 because we can't simply just short out the dependent voltage source. Okay, that's going to eliminate one of the relationships that's within the circuit, and that's going to skew the answer. So we have to do it a slightly different way. And so now we sort of get more into the nuts and bolts here. All right, so we have this circuit, and like I said before, the problems that exist, we can still use the open circuit method to find VTH. That's no problem. So we're going to do that the same way that we have done it before. RS, however, right, that is not going to work. We cannot just get rid of the sources. So how can we solve for RS? what we're going to do is use a different kind of load condition. We're going to short the terminals, and that's going to allow us to work backward and figure out what RS is. Because if you look here, again, going back to the circuit, let's say we figure out VTH using our open circuit method. Okay, so we're going to do that first. Let's do that one first. We get a value of 5 volts, whatever it may be. Then I short the terminals together. And then I observe and I calculate what IL is. So if I know that this is 5 volts and I know that this is 5 amps, what does RS have to be? Right, the voltage divided by the current will give you the resistance. So if it's 5 volts, 5 amps, give you 1 ohm. Right? So, so that's how we're going to do it. We're going to use the short circuit test to give us the current flowing through RS, and then we can use that to go back and calculate what RS is. So it's a little bit more calculation. We have to solve for 2 versions of the circuit as opposed to 1. All right. And so what I'm going to do, we can do these in any order we want. I was, for the purposes of explanation, saying that we should do VTH, the open circuit test, first, but in reality, you can't calculate RS till you have both the values. So we'll go ahead and do the short circuit test first. All right, so we have this circuit. We're trying to find the equivalent for what's in the orange, and this is what the circuit looks like once we apply the short. So that 2 kilo ohm resistor is gonna go away. Here, we are going to have to call back to some of our, work from previous chapters, because we need to solve this. We need to figure out what this current is right here. We want this. I'm going to call this IL short circuit, and this is the important value that we're looking for. All right. So, how do we do this? And the reason why I'm moving from step 1 to step A is because, right, this is like sort of a mini step within step number 1. We have to use either nodal or mesh analysis in order to solve. So we're going to use nodal analysis to solve. All right. So how many nodes do we have? I'm going to fly through this because I'm hoping by now that everybody's pretty well adept at this. Remember what I said about the midterm. If you're still having issues with the nodal analysis or the mesh analysis, you really need to go back and take a look at it. Yes?
Are we not counting the 2 K ohm resistor anymore?
Yeah, that's shorted out, so that's not going to have any effect. All right, so how many nodes do we have here? We have 1, 2, and then, right, essentially because this is shorted, this all becomes, everything in the green becomes 1 node. So we have 1, 2, 3 nodes that we're solving for, right? So answer 3. V1 is known. V3 is going to be our reference. So we only need to solve for V2 in order to complete this part of the problem. All right, so next step, let's solve for V2. And what we need to do is go down that rabbit hole like we have done so many times before. We start off with the basic expression, and then we fill it in with Ohm's law or whatever we need to do in order to solve. Normally when we're doing nodal analysis, what is our base equation for each node? It's KCL, okay? But again, if you remember going back to chapter 3 stuff, when we have a dependent voltage source there, like we do at node number 2, we can't do it that way, so we are going to use the expression for the dependent voltage source, which looks like this. So V2 is equal to 2 times Vx. All right, and so Vx is this voltage right here. And so this current right here I could call I31, which, well, actually I don't need to write it like that. The better thing to say is that Vx is equal to V3 minus V1, right? That's probably the more useful expression. Okay, so we have 2 times V3 minus V1. Bless you. All right, so V3 goes away. It's equal to 0, and V1 is known. V1 is 5 volts. So this is not too difficult of a nodal analysis. What we'll be left with is V2 is equal to 10 volts. Negative 10 volts, because I forgot about that negative right there. Okay. And then we still haven't completely finished because we're not really concerned with V2. We want to solve for IL short circuit. Okay, so IL short circuit is going to be equal to the sum of I13 and I23, right? If you take those two currents right there, actually, no. Hold on one second. No, that's right. Okay. So, so what we have is I13 plus I, so IL short circuit is equal to I13 plus I23. I'll go ahead and substitute in for Ohm's law, so that will give me V1 minus V3 over, so for I13 it's a 1 kilo ohm resistor, and then we have V2 minus V3 over what's another 1 kilo ohm resistor. Those go away, which leaves us with V1 over 1000 plus V2 over 1000, and so that's 5 milliamps minus 10 milliamps, which equals negative 5 milliamps. All right, so that is the answer to this step 1. ILSC equals 5 milliamps All right, next. So all three of these steps, right, just realize they're part of step number one. They're like little mini steps. Okay, step two is going to be to calculate VL open circuit, which is equal to V Thevenin. All right. So hopefully you're seeing here that we're building upon Chapter 3 stuff. If you know how to do your nodal analysis or your mesh analysis pretty flawlessly, then there's very little new here, right? It's just two different versions of the same thing. All right, so let's redraw the circuit. My ongoing thing with getting the paste to work. Come on, just do it. All right, I'm going to try one more time and then I'll have to redraw it. Okay, copy. All right. Sorry. One of these days I'm going to learn how to do it right. Okay, whatever. All right, so I'll just redraw it. Actually, we don't need to redraw. We can just keep referring back up above. So this is the circuit in, this is the open circuit condition, right? There's no load here at VL. So we just need to analyze, that. And so we'll go ahead and we'll use nodal analysis again. So calculate VOC equals VTH. For this, we will use nodal analysis. Okay. How many nodes? If we go back up here, there's 1, 2, 3, 4 nodes. So we have one more node because there's no short there to take away the two nodes. So going back down here, 4. Again, V1 is known. V4 will be our reference. So we need to calculate V3 and V2 if necessary, right? We're only concerned with the open circuit output or load voltage. So we don't really need to come up with V2 if we don't need it. I assume that we'll probably need to because we won't be able to get V3 without it, but we could do it without it. All right, so step A, again, we're doing like little mini steps in here. So step A, let's write out write the equations that describe nodes 2 and 3. I'd like for you all, well, node 2 we've already done, so we're going to use that same expression again. V2 equals 2 times Vx, which is equal to 2 times V3 minus V1. In this case, V3 is not the reference, so we can't just get rid of it. What's going to be our equation for node number 3? Yeah.
So like, how would do it? I would start off with the I, so I would do like I 1, 3,
Exactly.
3 minus I 3, 4.
Yeah. So the short answer, you're exactly right, but the short answer is KCL is what we're going to apply, right? Because we're doing nodal analysis. There's no voltage source at that node. So, like you said, right, we're going to use nodal analysis. So I'll label these real quick. I13 again, I23, I34. All right, so we know that I13 plus I23 equals I34. And if we substitute in there, what we'll have is V1 minus V3 over 1,000 plus V2 minus V3 over 1,000. All right, so we should be able to use substitution to solve for that, or we could use a matrix form, but we need, so one last thing we need to do is we also need to substitute this. We need to use Ohm's law there. So what I'm going to do is I'm going to switch this up a little bit. I'm going to put this all on one side of the equation. So I'm going to make this minus minus equals. And then so what we have is V3 minus V4 over, what's that? 2,000. And then now both of these will become minuses. All right. Okay. So now we're going to do the same steps we've done with any nodal analysis. This is going to be a lot of repetition. Step B. Group equations by V1, V2, and V3. So what we're going to end up with is this right here. We'll end up with equation 2 will be minus 2V1 minus V2 plus 2V3 equals 0. Equation 3 will be V1 times negative 1 over 1,000 plus V2 negative 1 over 1,000 plus V3, 1 over 1,000 plus 1 over 1,000 plus 1 over 2,000 equals 0. Right, what we did was, again, just repeating for 1 second, we moved the known values to the other side, which were the 10 and the 5 over 1,000. We put the system into a matrix form, and then we solved. And so what we see is that this value down here, this is our VTH. So that's the value that we were looking for to begin with. And so what that means is that we have both what we need. So the last step here, which I guess will be called step 3, is just going to be to, show the Thevenin source. And there's no need to draw it. You know what it looks like. But V Thevenin will be equal to negative 10 volts. Our RS, well, we don't know that yet. Actually, so we do have something to do here. We have to calculate RS from VL open circuit, which is the same as V Thevenin, and our IL short circuit. Right? So VL open circuit is negative 10 volts. IL short circuit will be equal to, or is equal to, negative 5 milliamps. And so lastly, that means our RS will be equal to VLOC over ILSC, which is equal to so that's our answer, 2 kiloohms. And so what we see is by doing it this way, we actually get the Norton and the Thevenin together, because what you'll see is that this is the same as our I Norton. This is the same as our V Thevenin. And this is the RS that we use in both. So we have here, and we have here. That's everything that we need. So that's how we solve for the Thevenin equivalent or the Norton equivalent for a circuit with independent and dependent sources. It requires a decent amount of work because you have to run the nodal analysis or mesh analysis twice. You are going to see a problem like this at some point, whether it's a quiz or an exam or whatever. So all I can say is when you see this type of problem is you have to, I don't know what the right word is, but you have to be methodical, keep both the parts separate, and just go through it, treat each one independently. Because if you think about it as having to do 2 nodal analysis problems back to back, or 2 mesh analysis problems back to back, it may seem like, oh man, this is a whole lot of work. Which it is. Anyway, when I give you this quiz problem, I'll have to probably give you a little bit of extra time to finish it off. Any questions, though? Yes?
This is still chapter 4, right?
No, this is 5.
This is 5, so this won't be on the quiz.
It's not on the quiz. The quiz is just on amplifiers.
Okay.
Yes? Same thing?
You might have said this, but how do you know you use V3 for the...
Yeah, that's a good question. So if you go back here, right, we're really looking for VL open circuit, which is the same as V34, which is V4 is 0. So that's the reason why it's V3. All right. So we're going to keep introducing new versions of this using examples. There's at least one more type that we have to deal with. And this one is actually not that bad. It's an example where we only have a dependent source. Okay? So what happens if we only have a dependent source? And what we're going to do is we're going to do a version of the problem that's very similar to the one that we just looked at, except we remove the independent source. So what we have is so this is 1 kilo ohm, this is 2 kilo ohms. Same values, 1 kilo ohm, 2 kilo ohm. This is going to be our, again, our VL that we're looking for. And we have the one last branch, which goes like this. Forgot the resistor. And this is 2 kilo as well. And so Vx is right there. This is 2 times Vx. So almost the exact same problem we had before. I'm just going to put make sure ... for that first step. Whenever you do these, make sure it's linear, make sure the dependent source refers to values that are inside the circuit, make sure there's only 2 terminals, etc., etc., etc. I do expect you to do those. Keep them in mind when you do a quiz or an exam problem. They are important. I could throw you a curveball and give you one that's not solvable, and in that case, you just write, can't find an equivalent, and you're done. Don't want to be spinning your wheels on a problem like that when you don't have to. This one fits all the requirements. So, next step. So, this is actually an easier problem because what we see is because no independent source exists, the Thevenin voltage equals 0. So half the problem is already solved. This is because no energy is injected into the circuit. All right, next. So actually, let me ask the question, what's next? Normally, right, what we would consider would be to zero out the sources. There are none anyway. We can't do that. Okay. No, because there are dependent sources, right? So the method that we used in the first problem was we zeroed out the sources and we solved for RS. We can't do that here. We have dependent sources. That's not going to work. It's the same thing we saw in the previous problem when we had independent and dependent sources. That doesn't work. So what about the other method? What about the short circuit test? Which is what we used in the last problem. Okay, and that also doesn't work because what we'll end up with is so to explain this second one, let's draw the what the equivalent would look like. So if we have an equivalent where this is 0 volts, and then we have a resistor here, and then we take a short circuit where this is IL short circuit, what is the IL short circuit going to be? 0 divided by the resistance, 0. So this whole thing here, this picture, backs up the second statement. Okay, so what we see is we have a weird situation. Both of the methods that we used in the first problem and the second problem, zeroing out the sources, find the equivalent resistance, that doesn't work. Doing the short circuit analysis, the method that we used in the previous problem, that also doesn't work, okay, for different reasons. So what is it that we can do? So the third method is going to be, and I'll just write it like this. So these two, this does not work, this does not work, this one, green, will work. No, no, yes. All right, so why will this work? Because, again, if I draw the same circuit I did a second ago, this is the Thevenin equivalent, and I attach to it another voltage source. So this is 0 volts, this is RS, and then now let's say I throw a 5-volt source on there. What will that current be? Right? You'll observe a current. You'll know what the voltage is at the terminals. You know the voltage at the terminals is 5 volts. you'll be able to calculate what the current is flowing through there. Let's say it's 5 amps. And so what does that tell you that RS is? This is 0. One ohm. Okay, so that's how we're going to get around this. We're going to attach an external source and observe the response, and what we're going to do is we're going to calculate it where RS will be equal to whatever the VL external is that we attach divided by the IL external that we observe. And, right, yeah, this is applied. And this is going to be observed. Or, since we're doing it using math, you could also say it's observed or calculated. Does that make sense? So we have 3 different ways. Pretty much we always find VTH the same way in all the problems. Okay? Open circuit test, except for the case where we have dependent sources only. In that case, it's 0. The funny part is, how do we calculate the RS? So the 3 methods are outlined here. Zero out the sources, calculate the equivalent. That works for the first one, doesn't work for the second and third. Short circuit analysis, that works for the second one, doesn't work for the third. And then now we come up with a third method, which is to attach this external source and do that. So let's go ahead and do that. So step number 3 is going to be attach an external source and calculate IL external. I don't know why I try every time. It's like, because one out of every 5th time it works. Man, whatever. All right. I just feel like I'm so close to understanding how it works. If you tap it, okay, copy I get. So then this. This is where it all falls apart.
You're trying to move it?
No, I'm trying to paste. Like, I should be able to just like push and like hold.
Could it be in the settings? Like, if you go to the top?
Well, I'm not going to figure that out right now. Ah, paste. Okay, so I need to go to not drawing mode. No, hold on. It did it. There we go. It moved. All right. We're getting somewhere. The most important takeaway from this class is going to be how to copy and paste onto the iPad. This is the big final exam problem. I'll hand out this iPad. You have to copy and paste something. All right. So let's apply our external source, which just goes at the terminals right there. And we're going to go ahead and use V external. Let me write the same way I did above. VL external equals 1 volt. Now, it doesn't really matter what value you use. You just need to use some value. That makes the math easy, hopefully. And we want to calculate what the IL external is. That's what we want. So, I'm not going to do any more nodal and mesh analyses for you, because I'm sure you're all fed up with it by now. So I'm actually going to skip the work on this one, the the mesh and nodal analysis. You know how to do it. Okay, I recommend that you take a look at it on your own. So, and I'm going to flip the direction just because that's the way I did it. So IL external is equal to 15 over 14 milliamps. And again, you are on your own to solve this. Shouldn't be anything more difficult than what you've seen before. So then step 4. Okay, what's our final result? What's Thevenin? What's Thevenin for any problem where we only have, yep, there we go, 0 volts. What is our RS going to be? Our RS is going to be the VL external divided by RIL external. You have to be careful with the direction of the current here because it's got to fit the passive sign convention for the RS value. And so we have 1 divided by 15 over 14 milliamps, and that gives us a value of 933.33 ohms. And that's it. So, quick review. Quick review of how we do each one of these problems. So we have different cases that we're concerned with. Okay, we have different methods. And then we have, the result is pretty much always the same 2 values, but we do know that, yes?
Sorry, for the problem before,
Mm-hmm.
is IL, is that equal to I Norton or whatever?
No, yeah. No, that's not. That was different when we were doing the short circuit test. That was from before. This one, it's not. Neither one of these values, VL external or IL external, doesn't have a direct relationship to either Thevenin or I Norton. In fact, I Norton is 0. If Thevenin is 0, then I Norton is 0.
So do you have to like specify that, or no? Like on the test report?
Yeah, we specify. We said Thevenin is 0.
No, I Norton. Because you said you wanted to break it up into two different.
Yeah, I mean, you could write both. I think, so I Norton is equal to Thevenin divided by RS, which equals 0 because Thevenin is 0. So I'm not, I mean, if I don't ask for both, I don't think I know that you know how to use Ohm's law to go back and forth between I Norton and Thevenin. So again, unless I ask for both of them, I don't need you to do both. Okay, so we should be able to do this review or summary here, and then that'll be it for today. Okay, so the first case is independent sources only. Okay, and so the method that we use is we find VOC equals V Thevenin using the open circuit test. Open circuit test. Step number 2 is we zero out the sources and find the RS equivalent. Right? And so the results we get are V Thevenin, which should not necessarily be equal to 0, and RS, which should not be necessarily equal to 0. Okay? Second case is when we have both independent and dependent sources. And for that one, we find VOC using the same, or find V Thevenin using the same method. So we find VOC equals VTH, again, the open circuit test. And I want to be careful to use the same notation. I called this VLOC, so let me use the same variable. The second step is we need to find ILSC, which is equal to the Norton equivalent current, which is the short circuit test. Right? And then 3 is we calculate RS is equal to VL open circuit divided by IL short circuit. And so what we end up with is VTH is not necessarily equal to 0. Or this third column is maybe a little bit excessive because the only time when it says anything interesting is in the last case. And then we get down to the third case, which is dependent sources only. So the first thing, probably the most notable thing here, is that V Thevenin will be equal to 0, right? And so our steps are going to be to apply VL external and solve for IL external. That's going to require us to use some sort of nodal or mesh analysis or whatever it is that you need. And then calculate RS is equal to VL external over IL external. So that table summarizes pretty much all of Chapter 5, or at least what we've done so far of Chapter 5. I think we're at the end, but I'm not 100% sure. You have 3 different cases that you're looking at. Unlike the mesh and nodal analysis, the current versus voltage source thing doesn't really make much of a difference. It's independent, dependent, or both. That's really where you have to figure out which method you're gonna use. This table is not necessarily going to be on the cheat sheet. Okay, so I do expect you to not memorize, but to understand how to solve. Now, one thing that I want to state is that this method also works for the first case. right? The open circuit and short circuit thing also works for the cases where there's independent sources only. We didn't do it that way, but. All right, so I think that's the end of chapter 5.